Okay, I want to finish up the notes on weathering. The first part of the notes, we talked a little bit more about weathering and erosion and also mechanical weathering. So the main thing to remember with mechanical weathering is the only thing that's changing is the size of the rock. The composition, the makeup of the rock is not changing. It's just the size. So I did that example where I tore up the piece of paper. I haven't changed the paper. I haven't changed the makeup of the paper. I've just changed the size of the paper. It's not a big piece of paper. Now it's a bunch of little pieces. So that's like mechanical weathering. Chemical weathering is the opposite. Chemical weathering, there is a change in composition. The minerals that make up the rock are different. They're changed. They've been exposed to a chemical of some sort. There's a chemical reaction that's taken place, and now the rock is different. So that's chemical weathering. It breaks down the rock, and then that can, be eroded and carried away and move someplace else. Right. So here are a few chemical reactions that can lead to chemical weathering. So hydrolysis, when things react with water, oxidation, they react with oxygen. Anytime in chemistry you see some sort of an ox like that, it's going to refer to oxygen. And then for what we're talking about, the third one, carbonic acid, that's probably the most important one for what we were talking about. So carbonic acid is formed when carbon dioxide molecules and water combine. The way this happens in nature, because it happens all the time, in labs and in plants where they make carbonated drinks, because any carbonated drink that you have has carbonic acid in it because carbon dioxide is put into water, so it forms. But carbonic acid is formed naturally in nature as rain and other water droplets in the air. But as rain is falling through the atmosphere, those raindrops will bump into carbon dioxide molecules, and those carbon dioxide molecules will go into the raindrop. Those carbon dioxide molecules then turn that raindrop into a very weak form of carbonic acid. So here's a picture of a cave. It's a specific type of cave. It's called a cenote. They're found in Central America. But basically, originally, this was all solid rock. But over, hundreds of thousands and millions of years, rainwater that is soaked down through the ground, that has been slightly acidic because carbonic acid's formed as the rain fell, has dissolved, and broken down, chemically weathered that rock and carried it away. So now there's an underground cave system, and then with a cenote, the part of the ceiling of the cave collapses, which leaves an opening into the cave system and the water below. So it's kind of an example. Over time, even though the carbonic acid that's in the rain is weak, given enough time, it can chemically weather and erode a lot of material. Same process forms acid rain. And something about acid rain, this is not something like in the movies where if it touches your skin, it's burning your skin and people are running and screaming, and it's just not like that. But with acid rain, if pollution is in the air, typically in areas where there's a lot of manufacturing and industrial processes, depending on the pollution that's in the air, as the raindrops fall through the air, it can collide with pollution, and then those different pollutant molecules can go into the raindrops and turn those acidic as well. So if it's something that's sulfurous, it can turn it into sulfuric acid, a weak sulfuric acid, or if nitrates, it can change those raindrops into nitric acid. So it's the same process. It's just if it's a pollutant versus just carbon dioxide or acid rain. So here we have an example, these two obelisks. So these large stone monuments that are super in Egypt. These were both made at the same time, same type of rock. They were in Egypt, and one of these, because it was a match set, one was taken to New York City. That's how it looks now. The main reason that the one in New York is so badly weathered is because there's water in New York. There's rain, there's snow, there's ice. There are other forms of chemical or of mechanical weathering, like frost wedging and ice wedging and that sort of thing. But the big thing is water. In Egypt, there's not a lot of water. There's not a lot of rain, so you don't have a lot of chemical weathering. In order to have chemical weathering, you have to have water. If there's no water, there's no chemical weathering, or very, very little. So it's not really something that needs to be worried about. So that's the big difference. All right, so things that affect the weathering speed. So how quickly a rock will weather in a road. Big things, climate. The temperature in an area and how much moisture. So again, if there's no water, then there's no chemical weathering. So if you don't have to worry about that, if you don't have to worry about chemical weathering, then that's going to slow down the whole weathering process immensely. So, areas where it's really hot all the time, you're not going to have a lot. Areas where it's cold all the time, not as much. Areas where it's, hot and cold, kind of like, here where we're at, times of the year it's above freezing, times it's below. That definitely adds to the amount of weathering that takes place. Another thing that affects how quickly weathering takes place is surface area. The more surface area there is, the faster the weathering. And surface area is just the amount of surface that's exposed to the outside world. So all of these groups of things, these blocks, they all have the same mass. But the third one has a lot more surface area. Or it's kind of like the concept of if you're cooking and let's say you're making mashed potatoes, or if you're trying to cook something more quickly, for mashed potatoes, you aren't just going to take the potato and put it in the water and boil it. I mean, you could, but it would cook a lot faster if you cut it up into pieces and put it in the water and cooked it. It's the same thing with weathering. The more surface area there is, the faster it's going to cook, or the faster it's going to weather. So it's the same concept. Another example is sugar dissolving in water. So, if there's a sugar packet with loose sugar and a sugar cube where that sugar is basically just compacted into a cube, if it was the same amount of sugar, you wanted to see which would dissolve completely first, it's going to be the sugar packet. As soon as you put those into water, in the sugar packet, every little crystal, water can get to it from all sides immediately. The sugar cube, water's going to have to soak through all the sugar on the outside until it can get to the sugar in the middle. So again, the more surface area, the more area that's exposed to the environment, it's going to make weathering take place that much faster. And then mineral strength. So depending on the differences in hardness of the minerals, that will affect the rate of weathering as well. So the harder a mineral is, the more durable it is, it's going to weather more slowly. If a mineral is softer, then it will weather more quickly. So limestone is cemented together with calcite. Granite has quartz in it. Quartz is much, much harder than calcite. If you've ever been to an old cemetery, you see old headstones that you can hardly even read, or maybe you can't even read them. You can tell that there used to be something there, but you can't tell what it was. They used to make headstones out of limestone because it's, as far as rocks go, it's relatively soft. It's, you know, pretty easy to work with, but it weathers fairly quickly. So some of those old headstones that, you know, have been exposed to, you know, the elements for, you know, 100+ years, you can't really read them very well, if at all. Now we make headstones out of granite, you know, which is a much harder and more durable rock. But that's kind of the reasoning why you can't read those headstones. All right, so I'm going to wrap that up. Yeah, have a good day.